Okay, good day. This is AP Calculus. I am Mr. McCully. This is the presentation on section 2.5, Implicit Differentiation. Let's get to it. Okay, we are going to be talking about implicit differentiation and implicit differentiation. And even though this is going to be a pretty short presentation, I've only got 3 examples and about 6 slides. The implications of implicit differentiation is very important, and it is something that we're going to use quite a bit throughout the remainder of the year. It is certainly heavily covered on the AP Calculus exam, and it's especially important when dealing with related rates, and there will be a lot of related rate stuff that you will have to be able to do. And it's probably one of the first really important applications that are, quote unquote, real world applications. So we are going to distinguish between explicit differentiation and implicit differentiation, and we're going to find the derivative of a function implicitly. Okay, so up until now, we've done only explicit differentiation. And so when you look at this expression here, it should be pretty self-explanatory, and we would just do the derivative like you've used so far. So this is an instance where we would have a constant multiple rule and a simple power rule, and we would just do the derivative of y. And so we would go 3 times the 2, reduce the exponent by 1, and then our value would be 6x. Now, implicit differentiation is functions and or expressions determined in terms of multiple variables. Now, this isn't technically a function because it's a circle, but you could solve it for y and do an explicit differentiation. But if we have a function that is defined in multiple variables, it may be easier to do implicit differentiation. And so the differentiation by any variable, so this case we did the derivative with respect to x, but that is not the only possible option. We could derive this function with respect to some other variable, and when we get to related rates, that variable is quite often going to be time, not just x. So a real quick example here. The implicit differentiation is very much related to the chain rule. And the chain rule we did in the last section, where we said that if we have the composition of 2 functions, in this case, the outer function, the x to the 4th function, and the inner function, the x squared plus x function, we could use the chain rule to do that derivative. And the way that we would do that is we would bring the 4 down, leaving the inside alone. Or I guess we could say we would do the derivative of the outside first, leaving the inside alone. And so in this particular case, we bring the 4 down, reduce the exponent by 1, we would leave the x squared plus 1 alone, and then we would multiply that by the derivative of what's inside, and the derivative of x squared is 2x, the derivative of x is 1. Implicit differentiation is quite similar to that. In this case, we, instead of some expression of x inside the function, we have this u. So the way you want to think of this u is there is a variable equation somewhere, u equals, that is in terms of x. That's how we think of it. So this x squared plus x and this u are certainly related in the context of this example. And so if I'm deriving with respect to x, the derivative of y with respect to x is just dy over dx. And so the derivative of u with respect to x, though, I have to apply the chain rule to it. And so again, I bring the 4 down, and I reduce the exponent by 1, and I leave the inside alone. But here, in the first example, I had a function of x, and I could do the derivative of that. Here, I don't have a function of x, I have a function of u, and I don't know how to do the derivative of it, but I still need the derivative of this inner function. So this du over dx is a placeholder that represents this 2x plus 1. All right. So whenever you do whenever you are deriving with respect to a variable, in this case x, and you come to a value that is different than that variable, you are going to have to apply some sort of chain rule and multiply by the derivative of whatever u is with respect to x. So some simple guidelines for implicit differentiation. This is from page 142 in the book. When you differentiate both sides of the equation with respect to x, and again, you don't always have to do x, it could be any variable, but just in this case, so that we stay consistent. When we derive with respect to x, we're going to collect all of our terms involving dy over dx on the left side of the equation. And then once we've done that, and again, so if all your dy over dx is on the left-hand side, that means everything else is on the right. And so once we have all of the terms of dy over dx on the left-hand side, we're going to factor out that dy over dx and then get it by itself, solving for dy over dx in the last step. So 3 quick examples. Here we have a equation that's a hyperbola, and we want to find dy over dx implicitly, and we could probably, again, solve this thing for y and do it explicitly as well if you wanted to check yourself. But I'm not going to. I'm just going to do, since this is a section on implicit differentiation, we are going to derive this with respect to x. So when I do the derivative of x squared, because those variables match up, I would do the derivative the way you would expect it to happen, just using the simple power rule. And that'll give me the 2x minus, now I'm deriving y with respect to x. So I have to think of y as some function of x. And so this is the composition of the x squared function with the inner function being the y function, whatever that is. So using the chain rule and the general power rule, I'm going to make it 2y. But again, I don't know what the derivative of y is, so I'm going to put this as a placeholder, dy over dx, the derivative of y. Since 25 is a constant, when I go to do that derivative, it doesn't matter what variable we're deriving with respect to, it's always going to be 0. So I've got 2 terms here. I've got a 2x, and then I've got negative 2y dy over dx. And so following the guidelines that we had in the last page, I want to collect all of my terms with dy over dx on the right-hand side, on the left-hand side. So I've got negative 2y dy over dx, and that's going to be equal to negative 2x. And then, so solving for dy over dx, I divide both sides by negative 2y. The negative 2's will cancel out and will just leave me with x over y. That is my derivative. Second example, page 142, number 34. Find the equation of the tangent line at the given point. Now, this is an instance. Since they're not asking for the derivative, they are asking for the equation of the tangent line. I just need to find the value of the derivative. So get to a point or do the derivative, but get to a point that you can use it, and then don't go any further. Just plug in and simplify. So if I am going to do the derivative of this function, and by the way, this is a circle. When I go and do the derivative of this function at 4, what I'm going to do is I'm going to, again, do some implicit differentiation. So I come to this first term here, and it'll be 2x plus 2, leave that alone, times, or well, I reduce the 2 to a 1, times the derivative of what's inside, and the derivative of x plus 2 is just 1, plus, now, this one is not in terms of x, so again, I'm going to use the general power rule here and bring down my 2, leave the inside alone, y plus 3, now to the first power, but I won't write it. And then the derivative of y is dy over dx. The derivative of 3 is 0, so I would leave it alone. And set that equal to the derivative of 37 is 0. All right, so now, yeah, I could solve for dy over dx, but this is the derivative. It's not pretty, but it is the derivative, and it's usable. So I'm going to plug in my 4, and my dy over dx will be the slope of the tangent line. So I'm going to go 2 times, 4 plus 2 is 6, times 1 is just whatever that will be. And then it'll be 2 times 7, because 4 plus 3 is 7 times dy over dx. and then it's still equal to 0. So now that's 12, that's 14. If I bring the I bring the 12 to the other side, I'll get 14 times dy over dx is equal to negative 12. And then dy over dx, that's not very good. Let's do a better job. Dx will be equal to negative 12 over 14, which ends up being negative 6 over 7. All right, so this, and let's not box that, negative 6 over 7. This is my slope of the tangent line. So I come over here, I use the point and the point slope formula, y minus 4 equaling to negative 6 over 7 times x minus 4. Distribute on the right-hand side, so I get negative 6 over, let's do it right. Negative 6 over 7x minus, now going to be plus because negative times a negative is a positive. And then 6 times 4 is 24, and that's all over 7. Now I'm going to have to bring this 4 to the other side through addition, so I need to change that so that I have sevenths. There are 28 sevenths in 4. So I've got y minus 28 over 7 is equal to the expression that we came up with. Add 28 to both sides, and I get y equals negative 6 over 7x plus 28 and 24 is 52. Yes, 52 over 7, and that is my final answer for that particular expression. Okay, last one. And I picked this one in especially because this is one that a lot of kids tend to miss on the quiz. They usually miss the fact that I see in this one, I'm going to have to use the product rule R-U-L-E, Macaulay, twice. If you look, I have the product of the function x squared and y, and then to that I have the product of the y squared and the x function. And so I have to use the product rule on this portion of the derivative and on this portion. So let's get to it. Let's derive with respect to x. And so just a real quick review of the product rule. Remember, if f of x is equal to g of x, h of x, then f prime of x is equal to g prime of x, h of x, plus g of x, h prime of x. All right, so doing the first one, the derivative of x squared is just 2x. We leave the second part of the function alone, so I get my y. Plus, I leave the first part alone, x squared, times the derivative of y. I don't know what that is, so dy over dx. Now I have completed the product rule for this first term here. Now for this second one, the derivative of y squared is going to be 2y times the derivative of whatever y is, times the second one left alone, plus the first one left alone, y squared, times the derivative of the second one, which is just be 1, and then the derivative of negative 2 is 0. All right, so simplifying just real quick here, 2xy plus x squared dy over dx plus 2xy dy over dx. I just used the property of commutativity of multiplication to reorder that one, and then y squared times 1 is just y squared equaling to 0. So I did that so I can show you that I have 1, 2, 3, and 4 terms in this particular equation. 2 of them have terms of dy over dx, and 2 of them don't. And so if we go back to the guidelines, we want to collect all of our terms of dy over dx on the left-hand side. They already are, but we do need to push everything else to the right-hand side. And since I have a positive in front of the 2xy and a positive in front of the y squared, they're going to be negative when I subtract them from the other side. So I've got x squared dy over dx plus 2xy dy over dx is going to be equal to negative 2xy, and it'll still be minus, sorry, y squared And then I don't want that bar there just yet. Minus y squared. All right, and so now it's a plus. Can't make that better. Okay, and so now, and this is going to be a technique that you use quite a bit, since I have all of my terms of dy over dx on the left-hand side, both of these two terms have dy over dx as a common factor. So I'm going to factor that out, dy over dx. And then when I take this first term and divide out dy over dx, I'll get x squared. And when I take the second term and I divide out dy over dx, I'll get 2xy. And that's still equal to negative 2xy minus y squared. And so now, since dy over dx is there, this is the only dy over dx, I can get it by itself by dividing both sides by the expression inside the parentheses. And so well, it's not my final answer, but dy over dx by itself is going to be negative 2xy minus y squared all over x squared plus 2xy. Now, we should look to see if we can reduce this. And I know sometimes we have problems reducing our fractions, especially when they have expressions in them. But let's look at this. I've got one term here, the negative 2xy. I've got one term here, the negative y squared, another term x squared, and then another term 2xy. These three terms here all have factors of y in them. These three terms here all have factors of x in them. These two factors have factors of 2 in them. But there is nothing in all four terms that have a common factor. Thus, this is my final answer for this expression, since I can't take anything out of all of the terms. Well, that's all I got today, folks. So the Star Wars fun fact of the day: in Phantom Menace, the Clone Wars, and the Revenge of the Sith, the opening crawl was created all inside computer with computer animation effects. But to get the opening crawl in the original trilogy, to get it so that the text slides up off into the distance as the opening music is playing. Well, the way that they actually did it was they made a plate of the words and they actually ran the camera over the plate of words. They didn't move the words, they moved the camera so that they could get that effect of it going off in the distance. And there's a picture of it. Well, folks, you have a great day. I will see you in class. Goodbye.